Today, I am going to tell you the story of how America copied Soviet jet engines, but missed the cooling system that made them indestructible. This is the tale of General Curtis LeMay, Soviet chief designer Vladimir Klimov, and Operation Moolah during the 1951 Korean air battles. But the truth was more overwhelming than anyone imagined. If you want to stand with our platoon and hear more epic stories, subscribe and join our ranks. Introduction and context. September 12, 1951. Kimpo Air Base, South Korea. Major Chuck Yeager climbed out of his F-86 Sabre after the most disturbing combat mission of his career. The Soviet MiG-15 he had engaged over the Yalu River hadn't just matched his aircraft's performance, it had exceeded it while demonstrating engine durability that seemed to defy the laws of thermodynamics. His own engine showed signs of thermal stress after just 90 minutes of combat operations, while enemy aircraft continued operating at maximum power for hours without apparent degradation. What Yeager couldn't have known was that the engine powering his adversary incorporated cooling technology that American engineers had dismissed as unnecessary Soviet complexity. For 5 years, U.S. intelligence had been analyzing captured German jet engine designs, assuming that both superpowers were building upon the same technological foundation. The reality was far more disturbing. Soviet engineers had independently developed thermal management systems that made their aircraft engines virtually indestructible under combat conditions. The implications were staggering. American jet engines were marvels of power and efficiency, producing more thrust per pound than any propulsion system in history. But they were also fragile, requiring extensive maintenance and frequent replacement due to thermal stress failures. Soviet engines produced slightly less peak power, but could operate continuously at maximum settings without the catastrophic failures that plagued American aircraft. The Korean War had revealed the fundamental difference between American and Soviet approaches to military technology. United States industry prioritized maximum performance and cutting-edge innovation, creating sophisticated systems that pushed the boundaries of engineering possibility. The Soviet Union emphasized reliability and operational endurance, accepting modest performance penalties to ensure their weapons could function under the worst possible conditions. By September 1951, American fighter pilots were reporting disturbing patterns in aerial combat over Korea. MiG-15 aircraft that should have been easy victories were proving remarkably difficult to defeat. More troubling, Soviet pilots were demonstrating tactical confidence that suggested their aircraft could sustain combat maneuvers that would destroy American engines within minutes. The intelligence picture was equally concerning. CIA operatives monitoring Soviet aircraft production estimated that Communist forces could maintain higher operational tempos than American squadrons because their engines required less maintenance and suffered fewer catastrophic failures. If accurate, these estimates suggested that Soviet air power could achieve strategic superiority through superior engineering rather than superior numbers. Strategic Air Command Chief General Curtis LeMay understood the implications better than most military leaders. The United States had invested billions of dollars developing the most powerful military aircraft in history, but those aircraft were proving vulnerable to enemy designs that emphasized durability over peak performance. The mathematics of air warfare were shifting away from technological sophistication toward operational reliability. The revelation would transform American aviation development and challenge fundamental assumptions about the relationship between innovation and military effectiveness. Soviet engineers had solved problems that American designers didn't even recognize existed, creating a technological advantage that could determine the outcome of the Cold War. Planning and Expectations. October 3, 1951. Pentagon, Washington, D.C. General Curtis LeMay stood before the Joint Chiefs of Staff presenting intelligence that would reshape American aviation strategy for the next decade. The classified briefing outlined disturbing evidence that Soviet jet engines incorporated design features that gave communist aircraft decisive advantages in sustained combat operations. The intelligence had been gathered through multiple sources: pilot debriefs, photographic reconnaissance, and, most critically, examination of crashed MiG-15 components recovered from North Korean battlefields. Each source confirmed the same conclusion: Soviet engines could operate at maximum power settings for periods that would destroy comparable American equipment within hours. "Gentlemen," LeMay declared with characteristic bluntness, "we have been building aircraft engines optimized for peacetime demonstration flights. The Soviets have been building engines optimized for war. Our pilots are flying aircraft that cannot sustain the power settings required for effective combat operations." The technical analysis was devastating. American jet engines like the General Electric J-47 powering the F-86 Sabre produced excellent thrust-to-weight ratios and fuel efficiency, but they incorporated single-point thermal failures that could catastrophically destroy the entire propulsion system if cooling systems were stressed beyond design limits. Soviet engines accepted weight penalties and complexity increases to eliminate these vulnerable failure modes. Air Force Chief of Staff General Hoyt Vandenberg authorized the most comprehensive reverse engineering program in military history. Operation Paperweight would coordinate intelligence collection, technical analysis, and industrial espionage to obtain complete specifications for Soviet jet engine technology. The program would operate under classifications exceeding those of nuclear weapons development. The decision reflected growing recognition that American technological superiority was not automatic. Soviet engineers had independently developed solutions to problems that American industry hadn't adequately addressed. The assumption that capitalist innovation would automatically exceed communist capabilities was proving dangerously naive in the face of combat reality. Pratt & Whitney chief engineer Arthur Kantrowitz was assigned to lead the technical analysis effort. His preliminary assessment of available intelligence was deeply disturbing. Soviet engines incorporate thermal management systems that appear to solve metallurgical problems we have considered unsolvable, given current material science limitations. The engineering philosophy differences were profound. American manufacturers emphasized maximum power output per unit weight, accepting reliability compromises to achieve superior performance specifications. Soviet designers prioritized continuous operation under maximum stress conditions, incorporating redundant cooling systems and thermal barriers that added weight but eliminated catastrophic failure modes. Intelligence indicated that Soviet manufacturing emphasized different priorities as well. American production focused on precise tolerances and sophisticated quality control to achieve optimal performance from each individual engine. Soviet production accepted broader tolerance ranges while incorporating robust design margins that allowed engines to function effectively even when manufacturing precision was imperfect. The strategic implications extended beyond aviation technology. If Soviet engineering philosophy could produce more operationally effective military systems despite lower peak performance specifications, the entire foundation of American defense planning required re-evaluation. The assumption that technological sophistication automatically translated to military superiority was proving incorrect in Korea's combat environment. Operation Paperweight would coordinate efforts across multiple agencies and private contractors. The CIA would manage intelligence collection and analysis. Air Force Technical Services would oversee reverse engineering efforts. Major aerospace contractors would attempt to replicate and improve upon Soviet innovations while maintaining production schedules for current American aircraft. The program's classified objectives were ambitious beyond anything previously attempted in peacetime. Complete technical analysis of Soviet engine cooling systems, Development of American equivalents that incorporated Soviet innovations while maintaining superior American manufacturing standards. Most critically, integration of improved thermal management into production aircraft before Soviet technological advantages could determine the outcome of the Korean conflict. Intelligence and Preparations. November 15, 1951. Wright-Patterson Air Force Base, Ohio. Dr. Sarah Morrison, the lead metallurgist for Operation Paperweight, examined components from a MiG-15 engine that had been recovered from a crashed aircraft near Pyongyang. Under high-powered magnification, each turbine blade revealed engineering decisions that challenged everything American industry believed about optimal jet engine design. The Soviet Klimov VK-1 engine incorporated cooling features that seemed almost primitive compared to elegant American solutions, yet performance data indicated these systems were far more effective under combat stress conditions. Instead of relying on sophisticated computer-controlled cooling systems, Soviet engineers had used purely mechanical solutions that could not fail due to electrical problems or software malfunctions. Most impressive were the turbine blade cooling channels that Soviet engineers had somehow manufactured using techniques American industry considered impossible given available technology. Each blade contained dozens of precisely sized passages that directed cooling air through complex internal geometries, providing thermal protection far exceeding anything achieved by American manufacturers. Morrison's analysis revealed the mathematical thinking behind Soviet design decisions. American engineers optimized for maximum efficiency under ideal operating conditions, assuming that sophisticated control systems could prevent thermal stress from exceeding design limits. Soviet engineers assumed that control systems would fail and designed cooling systems that could protect engines even under the worst possible thermal stress conditions. The intelligence picture was completed by information from Operation Moolah, a classified CIA program offering massive financial rewards to enemy pilots who defected with intact aircraft. The first complete MiG-15 obtained through this program provided unprecedented insight into Soviet engineering capabilities and manufacturing techniques. Technical analysis of the intact aircraft revealed systematic design choices that prioritized combat survivability over peacetime performance metrics. Soviet engines incorporated multiple redundant cooling systems that could maintain safe operating temperatures even if primary thermal management systems were damaged by combat or mechanical failure. American engines relied on single cooling systems that could cause catastrophic failure if compromised. The cooling channel manufacturing represented perhaps the most impressive Soviet achievement. American engineers had attempted to create similar internal cooling passages, but had been defeated by metallurgical challenges and manufacturing limitations. Soviet engineers had solved these problems using techniques that remained mysterious even after extensive analysis of recovered components. Dr. Konstantin Petrov, a Soviet defector who had worked on military engine development before escaping to the West in 1950, provided crucial insights into the decision-making process that had driven Soviet thermal management innovations. American engineers designed for laboratory conditions, Petrov explained during classified debriefing sessions. Soviet engineers designed for battlefield conditions. We assume everything will be damaged, contaminated, or stressed beyond specifications. American systems fail when these assumptions prove correct. Though the philosophical differences reflected broader Cold War ideologies about technological risk and operational requirements. American industry embodied capitalist principles of efficiency and optimization, creating sophisticated systems that performed excellently under ideal conditions. Soviet industry reflected communist principles of redundancy and collective security, accepting complexity penalties to ensure systems would function under the worst possible circumstances. Operation Paperweight engineers began attempting to reverse engineer Soviet cooling technologies using American manufacturing capabilities and materials science. The challenge was formidable, replicating design features whose manufacturing processes remained unknown using industrial techniques that had proved inadequate for creating similar systems. Initial attempts to recreate Soviet cooling channels using conventional American manufacturing methods resulted in spectacular failures. Turbine blades cracked under thermal stress, cooling passages became blocked by metallurgical impurities, and thermal barriers failed after brief exposure to combat-level operating temperatures. Soviet engineers had clearly solved fundamental materials science problems that continued to challenge American industry. The broader intelligence assessment painted an uncomfortable picture of American technological assumptions. The United States had superior manufacturing precision, better quality control systems, and more sophisticated design tools than the Soviet Union. But Soviet engineers had identified and solved critical problems that American designers had not adequately addressed despite possessing superior industrial capabilities. Opening actions. December 7, 1951. Classified facility. Wright-Patterson Air Force Base. Arthur Kantrowitz stood before the most complete Soviet jet engine ever obtained by American intelligence services, studying the cooling system that had revolutionized military aviation without American engineers realizing such innovations were possible. The Klimov VK-1 engine had been flown to Ohio aboard a specially modified transport aircraft following the successful defection of a North Korean pilot who had been promised enough money to live comfortably for the rest of his life. The engine before him represented 5 years of Soviet development that had proceeded independently of Western influence, incorporating solutions to problems American industry was just beginning to recognize. Each component revealed design decisions that prioritized combat effectiveness over the performance metrics that dominated American engineering evaluation criteria. Kantrowitz's initial examination confirmed the most disturbing intelligence assessments. Soviet turbine blades incorporated cooling channels that provided thermal protection far exceeding anything American manufacturers had achieved despite years of development and billions of dollars in research investment. The manufacturing techniques required to create these channels remained completely mysterious. The cooling system architecture was equally impressive. Instead of relying on single high-performance cooling circuits like American engines, the Soviet design incorporated multiple independent cooling systems that could maintain safe operating temperatures even if several primary systems failed simultaneously. The approach sacrificed some efficiency, but provided operational reliability that American engines could not match. Most significantly, all critical cooling functions were controlled by purely mechanical systems that required no electrical power or computer control. If the aircraft lost all electrical power, suffered electromagnetic damage, or experienced electronic failures, the cooling systems would continue operating automatically using springs, valves, and mechanical regulators that could not fail due to technological complexity. The contrast with American engineering philosophy was stark. United States manufacturers had developed sophisticated electronic cooling control systems that optimized thermal management based on real-time sensor data and computer analysis. These systems achieved superior efficiency under normal conditions, but could fail catastrophically if electronic components were damaged or if operating conditions exceeded programmed parameters. Test cell operations began immediately with Soviet engine components subjected to stress conditions that routinely destroyed American equivalents. The results were remarkable. Soviet turbine blades continued operating effectively at temperatures that would melt American components within minutes. More importantly, they maintained structural integrity even when cooling systems were deliberately damaged or disabled. Dr. Morrison's metallurgical analysis revealed sophisticated materials science that somehow achieved superior thermal properties using alloys that appeared less advanced than American equivalents. Soviet engineers had clearly developed heat treatment processes and alloying techniques that produced better results, despite using seemingly inferior base materials and manufacturing equipment. The testing program expanded rapidly as Air Force Technical Services recognized the scope of Soviet innovations. Complete engine test runs demonstrated operational capabilities that exceeded American performance under combat stress conditions while using less sophisticated fuel control systems and requiring significantly less maintenance between operational cycles. Intelligence continued flowing from multiple sources as Operation Moolah achieved additional successes. 3 more intact MiG-15 aircraft reached American control during the final months of 1951, providing comprehensive technical intelligence on Soviet aviation capabilities and manufacturing techniques. Each aircraft confirmed the same pattern. Soviet engineers had systematically solved reliability problems that continued to plague American military aviation despite superior industrial capabilities and larger research budgets. The implications for American air superiority were becoming impossible to ignore. Flight testing of captured MiG-15 aircraft began at Edwards Air Force Base under the highest security classifications. American test pilots reported aircraft performance characteristics that seemed to violate established principles of aerodynamic efficiency and engine power management. Soviet aircraft could sustain combat maneuvers that would destroy American engines while maintaining power output that should have been impossible given their apparent technological sophistication. The revelation was transformative for American aviation strategy. The United States had assumed that superior industrial capabilities and technological innovation would automatically produce superior military aircraft. The evidence from Korea suggested that Soviet engineering philosophy might be more effective for combat operations despite appearing less sophisticated by traditional American evaluation criteria. Most disturbing was the recognition that American pilots were flying aircraft with fundamental design limitations that Soviet engineers had systematically avoided. Every F-86 Sabre represented millions of dollars in development costs and sophisticated manufacturing, yet each aircraft incorporated thermal management systems that were demonstrably inferior to Soviet equivalents. The mathematics of air warfare were shifting in favor of operational reliability over peak performance specifications. Soviet aircraft that could sustain maximum power output for entire combat missions were proving more effective than American aircraft that could achieve higher maximum performance for brief periods before requiring reduced power settings to prevent thermal damage. As 1951 ended, Operation Paperweight had assembled the most comprehensive technical intelligence on enemy military technology ever obtained during wartime. The analysis revealed uncomfortable truths about American technological assumptions and the effectiveness of Soviet engineering approaches that prioritized combat survivability over peacetime performance metrics. The critical moment. January 8, 1952, Edwards Air Force Base, California. Test pilot Major Bill Bridgman pushed the captured MiG-15 to maximum power settings during the most important flight test in American aviation history. For 45 minutes, the Soviet aircraft had maintained combat power levels that would have destroyed an F-86 Sabre engine within 20 minutes. The engine temperature gauges showed readings that should have triggered emergency shutdown procedures, yet the power plant continued operating smoothly. Ground control monitored telemetry that challenged every assumption about jet engine thermal limits. The Soviet cooling system was maintaining safe turbine blade temperatures despite operating conditions that exceeded design specifications for any American engine. Most remarkably, fuel consumption remained stable, and power output showed no degradation even after extended maximum power operations. Edwards control. This is impossible. Bridgman's voice crackled over the radio. Engine temperature readings indicate catastrophic thermal stress, but performance remains nominal. Soviet cooling systems are functioning far beyond anything we considered achievable. The test flight data would revolutionize American understanding of jet engine thermal management. Soviet engineers had not simply built better cooling systems, they had redefined the fundamental relationship between engine power and thermal stress through innovations that American industry had considered theoretically impossible. Dr. Kantrowitz watched the telemetry displays with growing amazement as the Soviet engine continued operations that would have melted American turbine blades. The cooling channel design was somehow providing thermal protection that exceeded every computer prediction based on known materials science and heat transfer principles. The moment of revelation came during post-flight engine inspection. Soviet turbine blades showed minimal thermal stress despite 45 minutes of maximum power operations. American equivalents would have required complete replacement after such testing. The metallurgical analysis revealed alloy compositions and heat treatment processes that produced thermal properties American industry could not duplicate. "Gentlemen," Kantrowitz announced to the assembled engineers, "we are witnessing thermal management technology that represents a fundamental breakthrough in materials science. Soviet engineers have solved problems we didn't know existed using techniques we cannot replicate." The implications extended far beyond individual engine performance. Soviet aircraft could sustain combat operations that were impossible for American fighters, providing tactical advantages that could determine the outcome of aerial warfare. The mathematics of air combat had shifted in favor of operational endurance over peak performance capabilities. Intelligence reports from Korea confirmed the test flight revelations. MiG-15 pilots were demonstrating tactical confidence that reflected superior engine reliability under combat stress. Soviet aircraft could engage in prolonged dogfights, execute high-power escape maneuvers, and maintain formation flights at power settings that would ground American squadrons within hours. The strategic transformation was profound. American air superiority had been built on technological sophistication and superior pilot training. Soviet engineering advances were neutralizing these advantages through operational capabilities that made sophisticated American aircraft less effective in sustained combat operations. Operation Paperweight entered emergency status as military leaders recognized the scope of Soviet technological advantages. The program that had begun as routine intelligence collection had revealed systematic American deficiencies in critical military technologies that could determine Cold War outcomes, immediate aftermath, and perspective. The test flight data from Edwards triggered the largest emergency engineering program in American aviation history. Major aerospace contractors received classified directives to immediately begin developing cooling systems based on Soviet innovations, with unlimited budgets and maximum priority classifications exceeding those of nuclear weapons development. General Electric Chief Engineer Dr. Robert Henderson's assessment was brutally honest about American technological deficiencies. Soviet thermal management represents advances in metallurgy and heat transfer that we have not achieved despite superior industrial capabilities and larger research investments. We must either replicate their innovations or accept permanent disadvantage in military aviation. Pratt & Whitney launched parallel development programs, attempting to reverse-engineer Soviet cooling channel manufacturing processes. Initial efforts failed catastrophically, as American manufacturing techniques proved inadequate for replicating the complex internal geometries that provided superior thermal protection in Soviet turbine blades. The metallurgical challenges were formidable. Soviet engineers had somehow achieved precision manufacturing of internal cooling passages using techniques that remained mysterious despite extensive analysis of recovered components. American attempts to create similar features resulted in structural failures, blocked cooling channels, and thermal barriers that provided inadequate protection. Dr. Morrison's materials analysis revealed systematic Soviet advances in alloy development and heat treatment that produced superior thermal properties using apparently inferior base materials. Soviet metallurgists have developed processes that achieve better results with worse raw materials. Her classified report concluded, their engineering philosophy emphasizes robust design margins rather than optimal material utilization. The philosophical differences became apparent through systematic comparison of design approaches. American engines were optimized for maximum efficiency under ideal operating conditions, incorporating sophisticated control systems that could prevent thermal stress if they functioned perfectly. Soviet engines were designed for worst-case scenarios, incorporating redundant protection systems that could maintain safe operations even when primary thermal management failed. The strategic implications were recognized at the highest levels of government. Secretary of Defense Robert Lovett's classified assessment to President Truman was unambiguous. Soviet advances in jet engine technology represent a potential shift in military aviation capabilities that could affect the global balance of power. American technological superiority is not automatic and requires immediate response to maintain strategic parity. Congressional appropriations for aerospace development increased dramatically as political leaders recognized the implications of Soviet technological advances. The assumption that American industry would automatically exceed communist capabilities was being challenged by combat evidence and technical analysis that revealed systematic Soviet advantages in critical military technologies. Intelligence indicated that Soviet engineers had achieved these advances through different development priorities rather than superior industrial capabilities. Where American manufacturers optimized for peacetime performance metrics, Soviet designers optimized for wartime operational requirements that emphasized reliability over sophistication. The transformation in American engineering thinking was profound. Operation Paperweight had revealed that technological superiority required understanding and addressing problems that competitors had identified and solved. Innovation alone was insufficient if it failed to address the most critical operational challenges. Strategic consequences. The broader implications extended throughout American military technology development. If Soviet engineers could achieve superior results in jet engine cooling systems, what other critical technologies might incorporate innovations that American industry had not developed? The questions drove intelligence collection priorities and research funding decisions for the remainder of the Cold War. By 1954, every major American jet engine incorporated design features based on Soviet thermal management innovations. Turbine blade cooling channels, redundant thermal protection systems, and mechanical backup controls became standard elements of American power plant development, dramatically improving operational reliability and combat effectiveness. The transformation represented a fundamental victory for Soviet engineering philosophy without Soviet leaders fully understanding their achievement. American military aviation became more reliable, more durable, and more operationally effective through adoption of communist design principles that emphasized survival over sophistication. The irony was complete when American engines incorporating Soviet innovations proved superior to contemporary Soviet designs during later Cold War confrontations. American industry had not only adopted Soviet thermal management technology, they had improved upon it through superior manufacturing precision and materials science capabilities. Defense spending patterns shifted toward operational effectiveness rather than peak performance specifications. Military contractors were evaluated based on system reliability under combat stress, rather than maximum capabilities under ideal test conditions. The mathematics of military technology acquisition had been permanently altered by recognition that Soviet approaches to some problems were demonstrably superior. Epilogue. The legacy of Operation Paperweight extends throughout modern aviation technology. Contemporary jet engines incorporate thermal management principles originally developed by Soviet engineers who prioritized combat survivability over peacetime performance metrics. The cooling systems that enable modern military aircraft to operate reliably under extreme conditions trace their conceptual origins to innovations discovered through Cold War intelligence operations. The broader lesson transcends aviation technology to fundamental questions about technological competition between rival systems. The assumption that one approach must be superior in all areas proved false when combat effectiveness was the ultimate measure of success. The most effective solutions combined the best innovations from both sides of the technological competition. Today, modern fighter aircraft incorporate design principles from both American and Soviet engineering traditions. Sophisticated performance optimization combines with robust operational reliability to create military systems superior to anything either superpower could achieve independently during the Cold War era. The story of American adoption of Soviet jet engine technology demonstrates that technological superiority requires continuous learning from competitors rather than assuming automatic advancement through independent development. In military technology, as in few other fields, pride could be fatal, and effectiveness required adopting the best ideas, regardless of their origin.